We present our work, iTACO, Interactable Digital Twins of Articulated Objects from Casually Captured RGBD Videos. Simulation for robots in digital 3D scenes enables scalable and safe testing prior to real-world deployment. However, such simulation requires reconstruction or modeling of realistic indoor environments. While there is much work on reconstructing 3D objects, the output is typically a static mesh, which is not interactable without significant labor-intensive annotation of each object's movable parts and articulation parameters. Unfortunately, prior work on articulated object reconstruction places many constraints on the input data. One family of prior work assumes pre-aligned observations of the object in multiple states are provided as input, which is impractical and unrealistic. Although the recent approach Robot See Robot Do, or RSRD, accepts videos as input, it requires a static camera to record the interaction video, which is hard to acquire with a handheld camera. Therefore, our goal is to reconstruct an articulated object from a casually captured RGBD video, showing how a person can manipulate the object's parts. Such videos can be easily acquired by novice operators with an RGBD camera and have fewer constraints. However, to achieve this goal, we need to handle significant additional challenges due to simultaneous camera and object motion. We develop a course-defined framework to tackle these challenges. We estimate pixel-level correspondences between pairs of frames in the input video. In parallel, we predict a video moving map. With feature matching in the static parts of the object, we estimate the relative camera pose between the two frames. After aligning observations to the same coordinate frame, we compute the transformation for the moving part using feature matching in the moving region. Finally, we estimate the articulation joint parameters by taking an arithmetic average of results across frame pairs in the video. A refinement module then adjusts these initial estimates. Intuitively, if the predictions are perfect, we can transform any observed point cloud to the initial state. It should align well with the surface of the object. We first do part segmentation for the video and compute the moving map. Concurrently, we align the object point cloud with the camera pose and segment it into static and moving parts. Then, we transform the moving part back to its initial state using the estimated joint parameters. By computing a single-direction chamfer distance to the surface point cloud, we can establish an end-to-end differentiable computation graph, enabling us to apply gradient-based optimization to optimize the predictions. As our task setting has not been previously explored, we first construct a benchmark with synthetic videos of articulated objects. We simulate the manipulation of articulated objects placed in a cuboidal environment. We first render multi-view RGBD images of the object at the initial state to generate an object surface point cloud. Then, we place two virtual cameras in front of the moving part of the object to record interaction videos from two different views. Synthetic videos provide ground truth information for object geometry, part segmentation, and articulation parameters, enabling systematic benchmarking. We evaluate our method and baselines on these videos. We find that retrieval-based articulated object modeling methods, such as articulate anything, often retrieve the wrong object. Moreover, the movable part and joint predictions deviate significantly from the ground truth. On the other hand, articulated object reconstruction from videos methods such as RSRD produces inaccurate articulation joint predictions, likely due to the impact of camera motion in the video. In contrast, our approach is robust and produces more accurate geometry and articulations. Additional results with different objects show that prior work can frequently produce highly inaccurate joint placements or fail to produce a reconstruction entirely. We also evaluate on real video data. Again, we observe that articulate anything struggles to retrieve suitable objects, particularly in the book test case. The reconstruction-based method RSRD frequently fails, as it cannot handle the significant camera motion and occlusions present in the input videos. In contrast, our approach produces plausible results and is more robust to these challenging aspects of casually captured videos. For more details, please refer to our paper. Thanks for your attention.